Okay, example number 1. Solve for an unknown side. So let's read that together. You've got the picture there, right? Do you have a picture?
Yes.
Yes, you have a picture. Good. So you can refer to the picture. There is a maple tree, a willow tree, and a sumac tree beside a river. And we need to determine the width of the river. So Naomi finds a willow tree and a maple tree that are directly across from each other on opposite shores. Then using a third tree on the shoreline, Naomi plants 2 stakes, A and B, and measures the distance shown. Find the width of the river using the information that Naomi found. Now, how are we going to find the width of this river? It turns out that we cannot easily identify that these triangles are similar. So we're given some helpful information. We're given some side lengths there. We're given SA, SB, and BM. We're also given that angle M is a right angle. But if we look over to the smaller triangle, there's no right angle given there. So we can't say without a doubt that these are similar triangles. But we identify another marking on the diagram, that is parallel lines. SA is parallel to MW. So the first step in solving this problem is showing that the triangles are indeed similar to each other. Okay, so step 1. Step 1. Show that triangle BAS is similar to, and when I name my next triangle, I want to make sure I'm doing it the right way with the letters that I actually think are connected. BMW. It's an expensive triangle. Okay. Now, how are we going to do that? We first need to show that our angles, that we have 3 sets of corresponding angles, and that will let us know that it's a similar triangle, right? If we have 3 sets, 3 pairs of equal angles, then we'll know for sure. So can anyone tell me 2 angles that they think are exactly the same? One from the small triangle, one from the big triangle? Sorry, can you say that again?
AS and MW.
So, angles. So angles are named after 3 letters with the angle in the middle.
Angle A is equal to angle W.
Good. Do we know that for sure?
For sure. Yes.
Angle B. Same as angle B.
I like Jonathan's strategy. Why not start with angle B? So we got angle ABS is
Same as
equal to WBM. How do we know that?
Because they're opposite angles.
Opposite angles. Okay, so you're always going to write your rationale right after your statement. Good, we've got opposite angles. Anything else? What about S and M? Can we say that they're both right angles?
Yeah. No.
How?
Because one of them is right, and the other one looks wrong. Oh, because they have the parallel things.
Because they're parallel, okay? Because WM is parallel to SA, we can say that. So the next thing we can talk about is angle BSA. BSA is equal to angle BMW. And our rationale says these are both 90 degrees because AS is parallel to WM. And I'm using my symbol for parallel there. AS is parallel to WM. That means they're both 90 degrees. If one is, then the other one must be. Well, last time we justified similar triangles, we proved the third angle as well. But we know that because there's 3 angles in each triangle and 2 of the angles are already equal, we know for sure that the third one is already going to be equal. So it turns out that having 2 pairs of equal angles is enough to justify similar triangles. Did you catch that? In every triangle, we know that if you already have two of the sides, the third one is just 180 minus those two. So if two of them are corresponding, if two of them are equal, then the third one must be equal. There's no other option. So we don't actually have to write it. We can go straight from here to say that triangle BAS is similar to triangle BMW. And the reason that we are allowed to say that is because use the word two pairs of corresponding angles are equal. Two pairs of corresponding angles are equal. So if two pairs of corresponding angles are equal, I know that the angles in the third pair are also equal. Now that we've satisfied the requirement of proving that these two triangles are similar, step number 2. And I'm going to clear this. Step 2. Find the scale factor. Step number 2, find the scale factor. Well, in order to find the scale factor, we first need to identify corresponding side lengths. So let's find some corresponding side lengths, because we know that the scale factor is going to be equal to the ratio between our corresponding side lengths. So somebody give me two corresponding side lengths that we already know in our diagram. Okay, we're given BM from the big triangle, and we're given BS from the little triangle. I'm just going to make a note beside that you should make also. The ratio made by corresponding sides gives the scale factor, comma, K. The ratio made by corresponding sides gives the scale factor K. So if we input our values for BM, what's the length of BM? 24. And the length of BS? 9.3. And we're remembering this is all done in meters. We're going to leave our units out during our calculations, but we do have to remember at the end that we're talking meters. So this tells us that each side in the larger triangle is 24 over 9.3. That's just a value, right? We'll just divide that out. It's that many times as long as the corresponding side in the smaller triangle. So each side length in the big triangle is 24 over 9.3 times larger than its corresponding side length in the little triangle. Each side length in the big triangle is 24 over 9.3 times larger than its corresponding side length in the little triangle. So we're not going to change this into a decimal right away, because what happens when we change things into a decimal and then we round it? It's less accurate. We lose information. Okay, so we're going to leave it like this for now, and we're going to work with it. And step 3 is simply using our scale factor to find the width of the river. Step 3. Find the width of the river. Well, what side length shows the width of the river? MW shows the width of the river, and what is its corresponding side length? It corresponds to side length AS. And the ratio between these two is going to be equal to the ratio that we found out. It's going to be equal to K, right? If K is equal to this ratio, then K is also equal to this ratio. So maybe we'll write K first. Equal to K. And now we simply sub in what we know. We leave MW. AS we're given is 8.4. And K we just found out in step 2 is 24 over 9.3. How do I use my algebra skills to solve this one? Multiply both sides by 8.4. So on the left, all I'm left with is MW. And on the right, we have 24 over 9.3 times 8.4. And we put that into our calculator carefully. You can do 24 times 8.4 and hit enter and then divide by 9.3. Or you can do 24 divided by 9.3, hit enter, and then hit times 8.4. Either way, you'll come out with our answer. It's a decimal, and we're going to round to the nearest meter. So you come out with 21.66, never ending. But everything is measured in meters, so it's reasonable to to round our answer to the nearest meters. And we also always finish with a corresponding statement. So our statement here at the end is, therefore, the width of the river is approximately 22 meters. Now we took a lot of notes in between our steps there, which made it seem really long and annoying, but really all we did is step 1, we proved that the triangles were similar using the properties of similar triangles and the information that was given in the diagram. Step 2, find the scale factor, which was really just a quick math calculation up here. And then step 3, use the scale factor to find the width of the river MW, the unknown side. Okay, example 2 asks, what is the relationship between the areas in each pair of similar figures? What is the relationship between the areas in each pair of similar figures? You have any idea?
Multiplied by 2.
Maybe multiplied by 2 because the scale factor is multiplied by 2? Is there any way that we could find the area of each figure?
Yeah.
Okay. How do we find the area of each figure?
Triangle half times base.
Nice. So in any triangle, the area is 1/2 times base times height. We'll do our small triangle in red on the board, and I'll do our large triangle in blue on the board. It's going to have the same formula to get its area. So let's look at our small triangle. What is the base of our small triangle? The base is 3, and what is the height of the small triangle? Yep. 4. You sure it's not 5? Of course it's not 5. That wouldn't be the height at all. That's the hypotenuse. Okay. I'm going to do my whole numbers first. So I've got 3 times 4 is 12 times a half is 6. Okay?
That's easy.
6 square units. No specific units are given. So it's just whatever units it's in, square. Alright, big triangle. What's the base? 6 and the height? Area? 24 square units. Now that we have the area of both triangles, can you see how they relate to each other? How much bigger is the big triangle?
4 times.
4 times bigger. Nice. The area of the large triangle is 4 times bigger, or 4 times the area. Let's do that. It's 4 times the area of the small triangle. So our scale factor is 2, but the area, the factor that gets the area from the small triangle to the large triangle, is 4. Let's go ahead and do the same thing with our rectangles. So in section 2 here, in picture 2, we're dealing with rectangles. What's the area of a rectangle? Length times width. Is that going to be the same for both rectangles? So same thing. I'll do the small rectangle in red and the large rectangle in blue. Length times width. And let's go to our small triangle. What's the length? What's the width? Yep, 3 times 2 or 2 times 3, doesn't matter. That equals 6. 6 square units. And looking across to our large rectangle, yeah, we've got 8 times 12 equals 96. Oh boy, how do those relate to each other?
16 times bigger.
Nice. The area of the larger rectangle is 16 times the area of the small rectangle.
That's just A. No, that's A.
Yep, that was just A for both shapes, for both diagrams. Alright. Keep that information in mind as we move to B on example 2. B asks, what is the scale factor for each pair of figures? What is the scale factor for the triangles? To get from the small triangle to the big triangle, the side lengths, right? It's 2. Okay, equals 2. Scale factor is talking about side lengths, remember? Yeah, bit of a tricky one. Going back to this. And in the second diagram, scale factor, how do the side lengths compare to each other to get from the small rectangle to the large rectangle? Four, right? I just take 2 times it by 4, I get 8. If I take 3 and times it by 4, I get 12. So the scale factor for the rectangles is just 4. Good. C. Now we're taking our knowledge of the factor that we used in area to get from small to big and the factor that we used, our scale factor, to get side length from small to big, and putting it together. It says compare your answers to parts A and B. So let's look first of all at our area of the larger triangle is 4 times, and our scale factor is 2. Okay? Now look at this. The area of the larger rectangle is 16 times the smaller rectangle, and the scale factor is 4. Is there any relationship between 4 and 2 that's the same as the relationship between 16 and 4? Ah, they're square numbers. Way to go. Okay. Which really, the ratio of the area over the scale factor is 4 over 2. That's not a good way to say it. Okay, you got it right with square. We'll stick with your answer. In both cases, we're going to write this and then I'll help you walk through it, even though you already kind of understand it. The ratio of the area of the larger figure to the area of the smaller figure is equal to the square of the scale factor k. Okay, let's pick that apart a little bit. So to get from, in our triangles, to get from the small to the big, we had 4 times. That's talking about area. So in both cases, the ratio of the area of the larger figure to the smaller figure, 24 over 6 is 4. Right? 24 over 6 is 4. And the scale factor squared is 4 for the triangles. 2 squared is 4. Same in the rectangles. The ratio of the larger area to the smaller area is 96 over 6, which is 16. That's the same as taking the scale factor and squaring it. Okay, so you're seeing a connection here that we're going to use in the next example. But we're going to be able to use the scale factor, which is meant for the sides of a figure, and we're going to be able to apply it to finding the area of a figure because it's just k squared in that case, to go from smaller to bigger. I think that we're understanding. Let's carry on to an example. Yep. Do you have space for notes on the bottom of what you just wrote?
No.
Yes.
That much? How much notes?
Lot 0.
Like this much?
No.
No, I have
I'm more than you did.
I'm like skimming the paper.
Okay, I'm going to take brief notes. Actually, never mind. The notes are on your back page, so don't even worry about it. Just flip the page, go to example 3, and we'll do example 3, and this time we're going to be using we're going to be finding the area using our scale factor. So example 3 says, solve for an unknown area. So we can use our ratios to solve for unknown side lengths. We know that. Now we're going to be able to apply them to use them to solve for unknown areas. So the shaded region is to be an industrial zone. So whatever they're doing, maybe they're going to build some factories or a car manufacturing plant in between Main Street, King Street, and the railway. They make a triangle. It's going to be an industrial zone. We need to find the area of the industrial zone, and we are told to assume that king and queen are parallel and that all the streets and the railroad tracks are perfectly straight lines. Okay, so go ahead and on your little diagram, your simplified diagram, add anything that's missing. Add the lengths if you need to know the lengths. And we're also going to label each of our angles, but copy my angles so that we end up with the same names for our line segments. So my picture is not going to be as pretty as yours. Okay, kind of looks a little bit like that. You're going to have Q, N, R, and then at the top K and G. And we always label our points with capital letters. Capital letters.
I saw in the book.
Okay, now that we have our simplified diagram and the things that we already know about it are labeled, we need to make sure that we can even use this strategy for finding area by showing that we have 2 similar triangles. Would anyone like to give me the first corresponding angles for showing that we have 2 similar triangles here? R. So angle G, R, K. is equal to angle QRN. How do we know that?
We're opposite angles.
Opposite angles. Anything else we know? What about angle K and angle N? Can we say that they're equal?
Yes, sure, because they're
Well, do you remember the word from
Parallel.
7.0?
Yeah.
Nobody remembers the word for angles that are like here and here? Zoom, zoom, zoom. They're called alternate angles. Alternate angles are equal.
You said you usually do the same letter for the middle, or is that for side lengths? Because it has RKG. And then
So, yep, labeling it RKG means that we're talking about this angle, and its corresponding angle in the other triangle is down here, RNQ. So these guys correspond. So the angle that's actually in question goes right in the middle there. The point that the angle happens at goes in the middle. Does that answer your question?
I was just
Similar triangles. Good. So we've shown that angle K corresponds to angle N. We've shown that angle R corresponds to angle R. So we're showing that we have two pairs of equal angles, which means that G and Q are also going to be equal because the sum of interior angles in a triangle is 180 degrees. So we can say that triangle KRG is similar to triangle NRQ. Since they're similar, all of our rules about similar triangles will apply, such as scale factor. Okay? And the reason here is corresponding angles are equal. So here, corresponding angles are equal. That's how we know it's similar. Corresponding angles are equal. So let's go ahead and find K. What's K? Do we have corresponding side lengths that will help us find K?
1 and 3.
Yeah, let's give them names first. So we've got KG and QN, which is 3 over 1, which is just 3. So we've got a scale factor of 3. And now we can find all of the missing information that we need, including the area. So we're trying to find the area of the big triangle. Do we know how to find the area of the small triangle? What's the area of a triangle, ladies and gentlemen? 1/2 base times height. Do we have all that information for the small triangle? Yep. What's the base? 1. What's the height? 1.4. All these little dots is not the way to do it. I'm going to put my multiplication in brackets. So all we have here is 1.4 cut in half, which is 0.7. So we have a scale factor of 0.7. So the area of the smaller triangle is 0.7 kilometers squared. 0.7 kilometers squared. Now, how does that area relate to the area of the larger triangle?
Small triangles 3 times smaller than the area of the big triangle.
Yeah, careful, because it's not just K, that would be side length. It's K squared. So this is the part you'll have to double check your key concepts on the back of your page when you practice your homework. But I'm going to write this for you. The area of the large triangle is equal to K squared times the area of the small triangle. Okay? So we found this out in our notes there in the other example, that this is how areas relate to each other. For side lengths, we would have the side length of the big triangle is equal to K times the corresponding side length of the little triangle, right? But now they don't relate just by multiplying by k, they relate by multiplying by k squared, because we're talking about area, and a connection there, area is always measured in square units. So a good way to remember it, area is measured in square units, so I take k and I square it, and I'll be good to go. So here we go, the area of the large triangle is 3, because that's k, squared, times 0.7, which is 9 times 0.7, which is 9 times 7, and then move the decimal one place. 6.3 kilometers squared. Now I've run out of space at the bottom, but you would add a final sentence which says the area of the industrial zone is 6.3 kilometers squared. Alright, please, before you do your homework, review the key concepts that are printed for you at the bottom there. Then you're looking at page 324, 5 through 9, which is just a continuation of the assignment that you were given the other day. And actually, if you finished all of it the other day, you're a couple questions ahead, because you went up to number 6. And tomorrow, we're looking at a totally different concept, so make sure you come knowing this stuff. Enjoy.